Welcome everyone. Good afternoon. My name is Arvind Krishnan and today's webinar is about using your existing analysis data that you already do during your design to manufacturing process and enhancing it with 3D printing capabilities. Seeing what else we can do with the combination of the two to get more results out of it and improve our process, reduce our time to market, create better testing prototypes. So we're going to go through some examples, look at some SOLIDWORKS models, and see how that benefits us. My name is Arvind Krishnan. I work as an applications engineer from our Dallas office. I've been with GoEngineer for the past almost 4 years now, and I focus on the analysis and 3D printing tools. For those who've attended a webinar before, you've probably seen the product development process. Our core expertise is in bringing best-in-class applications right from the conceptualize phase to the manufacturing phase. So either it's 3D scanning and industrial designer in the conceptualize phase, followed by actually creating your designs using SolidWorks and electrical and PCB and other tools. Once you do that, you're going to validate your tools with either simulation, plastics, CFD analysis like Flow, Composer for documentation purposes, and through the process, you're also going to go ahead and then manufacture using CAMWorks, things like that. 3D printing plays a big part, and most of these tools are virtual, but with printing, you actually create a physical prototype. And that's what that plays a part in the entire process. Today, we are going to focus on the validation and see how 3D printing can help us in this specific field. Okay. So once again, this presentation focuses on the validation and getting more out of your simulation data, whether it's simulation or plastics or CFD. So in outline, we'll start with tooling, how you can go from a design to manufacturing process in the tooling, and look at an injection molding case study. Then we look at printing results with flow simulation or SolidWorks structural analysis. And finally, we'll talk about functional prototyping, how you can take some of your results, some of your deformed shapes, and really do more with it in the beta testing or the testing phase. See if there's more collaboration to save time and money. So the functional prototyping is going to be your biggest takeaway from this. In terms of tooling, we're going to look at an injection molding case study. We're going to use plastics with this. So here's an example that I did here in the Dallas office. Quickly switching to SolidWorks itself. Here's a key fob holder that the basic design intent was to have a key just fit inside of it and stick in the dash of a car with a Velcro on the back. So created a nice simple design with the GoEngineer logo on it and did a plastics analysis on this. So here is our SolidWorks interface with the part design to completion. And we're going to quickly switch to plastics. A solid mesh was used with additional mesh elements across some of the intricate geometry areas. The SolidWorks Plastics has an extensive database of about 4,000 different materials. This database is very useful because it is very the data that's needed for SolidWorks Plastics and for a material involves rheology testing, and there's a lot of data involved. So having an extensive database from plastics manufacturers all over the world is very useful. So we picked a DuPont material, and next is the injection location. a point at the back is selected. Once again, I thought of applying a Velcro on the back, so I didn't think that this point could be seen, and hence, as a first pass, I decided to select that point for my injection location. And I've run this analysis to completion. Let's go ahead and look at some of the flow results. So here's the flow simulation analysis, and we can see how the part fills to completion. If we dig a little bit more into some of the results, let's first look at the pressure setting. It's about 11 megapascals, which for the machine that I'm going to be using, which we'll talk about soon, this is a little bit higher than what I could do. Also, if you look at some of the weld lines, it goes right through the logo, which we would ideally like to be cosmetically more pleasing. So there are some design changes that are needed. Alternatively, if I look at the air traps as well, there are some air traps, there are many air traps, and venting all of these out would be a tough process. So obviously some design changes are needed here. So I made a couple of changes to the main design itself. Went ahead and made it a little bit smaller so that the maximum pressure isn't this big. And switching to SOLIDWORKS again, did make it a little bit more rounded. You can see more fillets in the bottom. Back to the same mesh with additional mesh control in some of the intricate regions. Material is still the same. This time, looking at the weld lines, I selected a injection location at the bottom. Okay. Now when we run this to completion, looking at some of the results. Now keep in mind, plastics does give you a whole host of different results. We're looking at a few of these. Here is how it fills, and if you notice the flow across the logo itself, it was one flow front that was going through it. So if you look at the weld lines, now the weld lines are in the peripheral regions, which are not as important from a aesthetic point of view. And also air traps are now in the peripheral regions or in the outsides where it can be easily vented. If I look at my pressure, it's about 40% of what it was before. The majority of that is because of the smaller size. So went ahead and designed a mold for this. Here's a 3-part mold. Let's go ahead and hide one of these so that we can see the insides. And we've created some bolt holes, and there's also some venting lines so that it actually vents to the outside. Switching back to the presentation, keeping that existing mold in mind, we went and used Stratasys' PolyJet technology, the Object 30 Pro machine. It has a 16 micron resolution, and a glossy finish option was used. With the glossy finish, the faces that are going to be touching the plastic part itself is going to be a lot more smoother and have a good glossy finish. I took this mold and used some injection molding material. Have a small hand press injection molding device in the back for some miniature testing, and using this, out came a plastic part that fit our design requirements. So with SOLIDWORKS' validation tools and with some of the printing capabilities with the Object PolyJet technology, you can combine your testing of tooling materials. We see a lot of 3D printers used for prototyping, but using 3D printers for tooling purposes and for understanding how your tooling should be made is another huge avenue where it's being used. We've also seen these printers and different parts being used for other traditional manufacturing processes like hydroforming as well. So it's a very beneficial application of 3D printing. Moving on. Next, we're going to look at printing result files itself. Here we're going to focus primarily on the flow simulation and finite element analysis results. The goal here really is to look at actually print your design in color with the different flow trajectories, as we're going to look at soon, or your stress results, deformation results, and analyze it as an engineering team together, looking at a 3D model as compared to looking at it on a 2D screen. Also, this is great for marketing purposes as well. Switching back to SOLIDWORKS real quick. Let's go ahead and close this model and open up the globe valve. This globe valve has one input on the left for water to come in. The valve itself is open about 50% and there's an exit on the right. So let's go ahead and turn on flow simulation. You can see the definition of the inlet and the outlet. And there are some goals for what precisely we're looking for from the results. So I'm going to go ahead and load up some results. Here's a cut plot on how the velocity distribution is. So it starts off relatively even, and then as it goes through the main region of the valve, there's some regions where the velocity is a lot higher as compared to some other regions where you're going to have vortices. And then it exits to the right. Another way of looking at this plot is by looking at the flow trajectory lines. This is the coolest part of flow simulation, where you can actually see a visual representation of how the flow goes from one end to the other. The colors represent the different speeds, and this is usually the coolest post-processing tool that is available in flow simulation. Well, these curves that it creates can be exported to the modeling side by using this little create curves option. Okay. Once you have these curves exported to SOLIDWORKS, you can use those curves and create solid bodies by using the sweep tool. So those curves actually become pipes with some diameter that you specify, and you would need to do that for each and every curve. So that's what helps you create the internal geometry, and then on the 3D printing side, you can specify the color of each of the different curves. Another feature in flow simulation is the option to check geometry. This is usually done before you start an analysis, and the check geometry is generally used for an internal analysis to check if the internal geometry is properly defined. This check geometry also has the option of creating a fluid body assembly. What this means is, whatever is my internal space where the fluid can move to, it's going to create a body, a solid body that represents that fluid region. So using that fluid body and combining it with these sweeps that we create with the curves, out comes an assembly that is now clear on the outside with curves represented on the inside for the different speeds. Using this and then being able to print this, you can create your complete, you can look at the results of this print using this option. So this can be saved as a VRML file by hitting File, Save As, and that helps you create the print file, and then you can go ahead and print it in a J750 or a Connex 3 machine. Once again, switching back to the presentation. Here is a rendering of the same file with all the different pipes on the inside. And this is the 3D printed file with, so this one was printed using the CONX3. The CONX3 has 3 colors, has a color palette with 3 base colors, and hence you don't see some of the red that would have been seen if we did it with a J750. But using the colors that we had in our palette, this is the print. Once again, it's clear on the outside with some post-processing and looks absolutely beautiful. You can do the same thing with finite element analysis as well, where you can look at a von Mises stress plot maybe and print it with the deformed shape and specify the color as a distribution. And this can be exported as a VRML as well. And analyze the results. So once again, with the ability to print results, you can take your 2D post-processing tools and make it 3D and analyze it as a team together, or you can also go ahead and use this for marketing purposes, where you can specify in a more vivid manner how your design is better than a competitor's, or specify your design intent with more clarity. Last point is functional prototyping. Now, as you can see, a helmet on the left that's been printed in a deformed shape. We're going to talk about that very soon. But functional prototyping with 3D printing really helps reduce your cost before, during your beta testing process. When your design is in the R&D facility and you're going through several iterations, the ability to just print something and functionally test it for form, fit, and function is huge and very beneficial. And that's what a lot of our users use 3D printing for. We're going to try to see how we can take this to the next level. First off, as of now, the results or the design that we have are printed. How about we print the actual results with deformed shapes? So let's start off with SOLIDWORKS plastics. Here's a propeller that is warped. Okay. First off, we can do warp analysis with plastics and export the deformed shape itself. Whenever you have warping, there is always some amount of, whenever you have a plastics injection molded part, there's always some amount of warping that is seen. You can reduce the warping, but you can never eliminate the warping completely. So quickly switching back to SOLIDWORKS. Here is the propeller. And let's go to plastics. Once again, mesh has been defined. Material and injection location have already been defined. Here is the mesh model with the 2 injection locations. A complete flow, pack, and warp analysis have been run. Let's go ahead and look at the warp results. Keep in mind, I have magnified these results by 3 times so that we can actually visually see it. And you can see how this warps out of shape a little bit. Now, owing to the locations I have selected, there is a slight asymmetry in the warpage itself. But these are the warp results of the part. And I can use these warp results and use the export option in SOLIDWORKS Plastics and export these results to an STL format, and then use the warp results as for my functional testing. So even before I create my mold and optimize my manufacturing process for this, I can actually go ahead and functionally test it because I have the warped shape already with me. So functional testing with the warped shape. From a structural point of view, this is beneficial as well, and we'll talk about that a little bit more. Quickly switching back to the presentation. Another huge benefit is the ability to apply a negative deformation factor. So let's think about this just for a minute. Okay, if you have an original shape and you see how it warps out of shape, in SolidWorks, you can now apply a negative warpage, a negative deformation value, so that whatever warpage you have, it's taking the negative of that, so that once you create the mold and injection mold this part, it warps back into shape. Now, I'd be the first one to say warpage is an extremely highly nonlinear process, and a -1 scale may not always work. But the idea is you have the capability of creating the inverse of a warped shape and designing your mold for it so that the part warps back into shape. Extremely beneficial in terms of reducing the effects of warpage and getting a part within your level of tolerance and maintaining the design intent that you have. Okay. Switching back to the presentation. From a structural analysis standpoint, you can also do functional testing with loads. Now, once again, prototyping, you want to check clearances, check the design intent and things like that. Testing of a lot of our designs can be very cost prohibitive, especially if it's a destructive testing where the part itself is being destroyed. Okay, imagine having even a static load on a part. Instead of actually applying that static load, you can just print the deformed shape of the part if it had a load, and then test your design with the deformed shape. Okay. We spoke about destructive testing. Anytime you have destructive testing or you have impact, analyzing the complex impact deformation is extremely tedious, not only from a testing perspective, because it's costly and it's time consuming, but also it's expensive to gather data when doing the testing. Because for a helmet, for example, so first off, this video on the left, courtesy YouTube, and I have a link to this. If anyone wants to see this, just Google or use YouTube and search helmet impact or helmet bullet, and this should pop up. But if you notice the video on the left, as soon as a bullet hits it, look at the waves that are generated through the helmet. And this requires a very slow motion video, which is expensive to generate, and it's a very destructive method of testing. Now, in no ways is anyone recommending to get rid of the testing process at all. Testing is extremely integral and is never replaced. The goal is to reduce the number of prototypes that are available with testing. So let's switch back to SolidWorks. Here is a helmet model. And a simulation has been run on this helmet model with an impact load. I'm going to go ahead and pull up some of the results. So first off, if you right click on the results box itself, you have the ability to create a deformed shape. Okay. Once again, this is a non-linear dynamic analysis, which means there are a whole host of different results and different deformation shapes based on how it deformed and at what time. The analysis itself was ran for about 0.03 seconds, which is an extremely small amount of time after impact. So you can save the deformed shape as a result itself, and then you can print it as an STL. Once you do that, you can then do your functional testing or even do your testing with that deformed shape. If you want the stress results and the color distribution of the results, you can right click on a particular plot and then use the save as option and then save it as a VRML file so that you now have the results overlaid on the deformed shape for the testing. Let's go ahead and look at an animation. I'm going to reduce the number of frames real quick. So you see the impact, and because of that, you see the actual moving of the helmet, and you see the propagation of the waves of stress through the part. Once again, extremely tough to test and record this behavior, and doing a simulation is very useful. But now you can actually do more with that simulation, because first thing is you get to analyze the results, test different materials, and analyze how different materials and different geometries behave at different times. And then you can actually print these results. You can actually print these results and test it on an actual 4-year-old or a 6-year-old or a 12-year-old and see how the deformed shape affects each one of them. So you're doing this testing of the form and the fit after without actually deforming it by hitting it with a ball or a bullet or another helmet, and testing the effects of it and the deformation of it before you have to actually do any testing in any destructive testing in real life. So those were some of the applications that I had in mind. We are getting close to the 2:30 deadline, but once again, to summarize, there's some real benefits in doing more with your simulation data that a lot of y'all are already using on the field before you do any testing, and there's a lot of possibilities in getting more out of that data and improving your testing capabilities by reducing the amount of time and also the costs, and overall the goal is to reduce your time to market. So once again, thank you. My name is Arvind, and you have my email address in the bottom if you have any questions. You feel free to connect with me on LinkedIn as well.